Hi, and welcome back to the Low Level Devel channel's Gameboy Emulator development series. In the previous video, we just started working on the PPU, just enough to get it to be able to display some debug information. In this video, we're going to start wiring up the LCD registers with the PPU and create a state machine for processing the different LCD states within the PPU. So let's get started. So let's start out by going back to the pandocs, and we're going to look up the registers for the LCD. You'll find them under this rendering section. Here, the very first one's going to be LCD control, which is at FF40. These are the different bits that can be set on that. We'll get into those later, but for right now I just want to kind of gather the different registers we need to set up. So yeah, let's go ahead and just create a header file where we can start storing them. So we'll create this as lcd.h. Do pragma once, include our common.h. And now we're going to create our LCD context. At the very top of the context, we're going to have the registers. We're going to put them in order that they actually are in the information. So let's start with LCD-C. That's at FF40. Let's see. And then the next one's going to be the LCD status register. Has these different bits to set, which again we'll get into later. So this is going to be LCD-S, we'll call it. And then after that comes some scrolling registers. We have our scroll Y and scroll X that are at FF42 and 43. And we'll create variables for those, scroll Y and scroll X. Alright, and let's see, then we have our LY register, which is essentially the current line that we are on, and our LYC, which is compare register, that will actually, if LYC equals Y, and the stat register flag is set, we can generate a stat interrupt based on that. So we'll have our LY, and we're LY, I'll just call it LY compare. So that takes us to 45. Now if you remember 46, let's go down into IO. Yeah, FF46 is our DMA. So we already know what that one is. Just add it here. Now let's go back, and to our palettes is where 47 starts. So FF47 is the background palette. 48 and 49 are the sprite palettes, otherwise known as OBG palettes. So you have two of them. So there's OBG palette 0 and 1. So we're going to create a background palette and then two OBG palettes. Okay, so that's 48, 49, and then back to 4A is our window Y and window X position. If you're not familiar with what the window is, we'll discuss that later in another video, but it's another scrolling section of the interface. So that's all of our registers, and they're in the order of the bus. So we'll put some other data here. So having them in that bus order will help us when reading and writing. So our other data, we're going to have the different palette colors. 4 colors for the background, 4 for sprite 1, and 4 for sprite 2. Sprite 2, sprite 1, OBJ 1, and OBJ 0 and OBJ 1 are essentially the same thing. So now if we look back at our pixel FIFO, this is where we go through different modes of the LCD. And it starts out in this OAM scan mode where it scans for the object attribute memory, scans for sprites and stuff. The next mode it goes into is where it's actually transferring pixels onto the LCD. It can be, there's a longest and a shortest value that it can be, but depending on what kind of calculations it has to do. After that it goes into mode 0, which is HBlank. So at this point a lot of more things are accessible to the game. And then eventually after line 143 it goes into this mode 1 vertical blank. So those are the 4 different modes that it can go into, and we're going to create an enumeration for each of those so we can track what mode we're in. We'll call this LCD mode. So we have mode HBlank, VBlank, OAM, and I'll call this one XVer for where we're transferring the pixels. So we're going to create a, let's see, a function LCD get context so we can access this context from other components. Then moving back over to our LCD control, I'm just going to copy and paste these into a comment so we can see them as we create some macros to access these values. Now hopefully you can see this. Some of this got cut off at the bottom, but let me create some macros. I'm going to start with one for the background enable. So I'm going to call LCDC BGW enable. And in order to get that, that's bit 0 down here. So in order to get to that, I'm going to use this bit. We'll say LCD get context. And we're going to get the LCDC bit 0. And that's all. So that's going to return the bit 0, which will tell us whether the background and window are enabled. I think I'm missing a parenthesis here. Nope, I think I just got one extra on the front. Okay. So that's going to be our first bit. The next one will be the object enable, which says where sprites are enabled. Okay, I'm just pasting that one in. That's essentially the same thing, but it's grabbing bit 1 instead of bit 0. The next one is going to be a little more complex. We're going to grab the object height is at bit 2. If it's 0, then it's going to be 8. If it's 1, then it's going to be 16. So now I'm just going to go through and paste the rest of these in. And you can see these are the same map, same way as we did on the previous ones. Okay, our map area, our LCD enable. Okay. So now the next one we want to go to is our status register. That's going to control some of these mode flags. So if we go through and go to the status register, copy this data. I'm just going to put it right over top of this other. And you see bit 0 and 1 is the mode flag. So that's going to tell us what mode the LCD is currently in. And I'm just pasting this in, or essentially grabbing the first 2 bits and casting it to LCD mode. Okay. And yep, cast it to LCD mode. So the next one is going to be our LYC flag, which says whether the LYC is set. Actually, let's first call a mode set. Yeah, let me resize this some. Mode set is going to actually first clear those 2 bottom bits, and then OR those 2 bottom bits with the mode that was passed in. Yeah. Okay, now we'll go to the LYC flag, which will be set if those values are equal. 0 if different, 1 if equal. And then again, those are going to be on the LCDS status register, and they're bit 2. Now the next 4 are going to be related to whether interrupts are enabled at different stages. Again, we'll create a set register for that one too. LYC set. So now these 4, that's going to be bit 6, 5, 4, 3. What we need to do is create an enumeration for each of these that'll make it easier for us to check the status of these different flags. So I'm gonna go up here, just paste it in, and these just represent shifting the bit over by this number. So 4 for VBlank, 5 for OAM, etc. And now we'll be able to use these in our macro to get the value of those. So if LYC is set, it'll and 1 shifted over by 6, and that'll tell us whether that interrupt source is enabled or not. Alright, so I'll get rid of this stuff. So now a couple of functions we need to add: the LCD init. We need a read and a write function as well to wire this up to the bus. Okay. So now let's move on to the implementation of it. So we're just going to create a lcd.c file in here. Put a couple of includes, lcd.h. We'll need the ppu.h, and I think we'll need interrupts too, and DMA. Yeah, DMA is probably enough. So now we're going to create our context, LCD context. I'm pasting in the colors here. These are the default colors, starting with white, a light gray, a darker gray, and a black. Okay, so now moving on, we'll start with our LCD init function. First we need to set some of the default values for some of these registers. For the LCDC, it's 0x91. Scroll X is 0, scroll Y we need to set to 0. LY and LY compare, both set to 0. And this background palette is set to FC, and the two object palettes are both set to FF. Now our WinY and WinX we're also setting to 0 by default. Now we're going to loop through each of these palette colors and set them to the default color. Okay. And now we're going to need to create our LCD get context. Just return the address of our CTX variable. And let me scroll up here. And to implement our read and write functions, since we have our registers in the order that they are on the bus, I'll scroll this up in just a second. Yeah, since we have these registers in order that they are on the bus, we'll be able to use that address. FF40 is our starting address. We're just going to grab the offset is address minus 0xFF40. Then we can convert our context into a byte array. U8 pointer. And just to return the byte array at that offset. That beats creating a bunch of if-else blocks. So now for our write method, bear with me here as it's cutting off at the bottom of the screen, but I'll scroll it up soon. We're essentially going to do the same thing to start out. And we can say p at offset equals value. But there's a couple other special things that we need to do. First off, if the offset is 6, that means we're at 0xFF46, which is DMA. So we need to do our DMA start. Okay, then there's a couple other scenarios. I'll scroll this up in a minute, but we need to also do some special handling for the palettes. So 47, 48, and 49. So if the addresses are in those ranges, we need to do some special processing. So 48 and 49 are both of the object palettes. So I'm going to say 0 and 1. 0, 1, and 2 are the three different palettes, 0 being the background, 1 and 2 being the two object palettes. So I need to create this function up here to update the palette based on the palette data passed in. So we'll say palette. So I'll start just creating a pointer to the colors because they're all going to work the same. So if 0 is passed in, we're going to use the background color. So if 0, if 1 or 2, I'll just use switch palette. In case it's 1, we're going to use p colors equals CTX SP1 colors. And in case it's 2, we'll use SP2 colors. Now we just need to set some values on these. So essentially we want to say p color 0 equals the colors default at index palette data, and then grab those bottom 2 bits. So the bottom 2 bits of palette data is going to infer our color 0. So hopefully that makes sense to you, because we're going to do the same thing for the other 3 colors. So for color 1, color 2, and color 3, but instead of the bottom 2 bits, we want to grab the next 2 bits. So I'm going to shift it over 2 bits, and then grab the bottom 2 bits again. Shift over 2, 4, and 6. That's going to give us our different palette colors for those specific palettes based on the default color set. So yeah, it's going to pull it right out of there. And that comes from the pan docs you'll see as well. There's another little stipulation here. Looking at this documentation, we'll see, again, this is where it denotes which of those bits are for which palette. So 0, 1, 2, and 3. Bits 0 and 1 are for color index 0. and then 3 and 2 for 1, 5 and 4 for 2, etc. So now the difference is on the two sprite colors, they have no white color, because if it's 0, then it's transparent color. So you can see that these work exactly like the background ones, except the lower 2 bits are ignored. And that's because of that transparent color. So instead of passing in value for these other two, we're actually going to AND off those last 2 bits. Okay. So that should be all that we need to start with the LCD. Now we can move on to wiring it up. So to start wiring it up, let's go over to our IO.C. So on our IO read, there's a couple of things we had here. First of all, this FF44 was a hack that we initially put in. What I want to do is copy this section, this between. I'll paste it down here. I'm going to say if it's between FF40 and FF4B, then we're going to do LCD read. And I should include lcd.h. Looks like I missed timer.h too, so I'm going to put that there. So that should be it for the read. And now for the write, remember we had this hack for DMA. You can take that out. I'm going to copy the timer one from here. 40 to 4B will be LCD write. So that's wiring it up to the bus at least. So which should give us a good start to be able to try things out. So first let me run through here. Yeah, we did have another, get rid of that little debug thing. And yeah, we should be ready to go. So let's try compiling this and see what happens. Just gonna clear. Let's do make. There are some warnings. I want to go through and just fix those. Looks like CPU.h was missing. What else? Yeah, that was it. So now let's try and run this, let's say against one of these. Okay, you can see that that ran until it halted. So we're still seeing our debug output, which is good. And let's try this on something else. Let's try it on a Dr. Mario. It looks like Dr. Mario's not running anything yet, so still have some more changes we need to make for that one to work properly. But at least we know it's running, so I can try some other ones here. Yeah, that one works too. Okay. Alright. And now that we have our CPU working fine and tested pretty well, we really don't need to see all that debug information, so let's go through and add let's see, a little check here. I'll create a defined CPU debug, set it to 0 for now. And I'll put it around, let's see, everything here. This is all just debug information. So if it's set to 1, then we'll do this. And so that'll pretty much comment all that out. You can see it's a lot less chatty, just our debug information that's being done there now. So if we do one that doesn't have it, we'll see no output. Dr. Mario again, it's not displaying any of the data yet because we don't have our PPU totally working yet. So let's go on into our PPU and continue on that. So we're going to start with creating a state machine to go through those different modes of the LCD. Not PPU. So we'll need to include our LCD.h, and we're going to include string.h because we need that for the mem set. And we're going to include this ppusm.h. That's a file that we need to create still. That's going to be our state machine. And the state machine's job is to run through these different modes. These are going to be the different states of the PPU, these different modes that it needs to run through. So let's create this PPU_SM header file. Pragma once. Includes here common.h. Now we're going to have our PPU mode OAM and essentially one function for each of these. So OAM, what do we have? Xfer, VBlank, and HBlank. Okay, so now we'll create our implementation for that. Or we can do that later. Let's continue on the PPU init function. So inside of our init function, there's a few things we'll need to do. First, let's actually create this PPU get context, because this is going to allow other components to use the PPU. I'll put that in its header as well. See down here. And let's see, actually while we're here, there's a couple other things we need to add to our PPU context as well. So right now we have our two different RAM types, but now we'll need to add some information about the LCD. First, actually, I'm going to put some constants up here. We have our lines per frame. There's 154 lines in a single frame. There's our ticks per line, 456. That comes from the pandocs here, where you see 456 dots for each of these lines. And the Y resolution and X resolution. And now we'll add these couple of variables. So we have the current frame. So that'll be the current frame that we're on. The line ticks, this is going to be how many ticks there are in the line currently. And then our video buffer. And that'll be where we actually end up drawing our pixels, which we're not doing yet in this video, but we're setting the stage for it. So in our PPU init, we need to set up some of those values. Current frame, we're starting at frame 0, of course. Line ticks, every line is going to start at line tick 0. Allocate some memory for our video buffer. So resolution times the bits per pixel. So then we're going to LCD init. Now we need to set the LCD mode. Remember, we start out in mode OAM. Okay. And let's go through and mem set some of these memory regions. So zero out the OAM RAM. And I'll zero out our video buffer as well. Times xres times size of U32. Okay, now we want to make sure that PPU init is called at startup. I'm going to put it in the CPU run, and I'll include ppu.h up here. So now getting into the PPU tick. So for every time it ticks, we want to increment the line ticks, and now we're going to switch the LCD mode. If you remember, that gives us the mode, the LCD. For mode OAM, we just simply call PPU mode OAM, and we do the same thing for each of them. Xfer, VBlank, call VBlank, HBlank, we call HBlank. So that'll be all for the PPU side. Now we should create the PPU underscore SM so we can implement the state machine. So to start with, we'll include ppu.h, lcd.h, and cpu.h, as well as interrupts.h. And now I'm just going to paste these into the implementation file. Alright. So each of these we want to implement here. We're starting with the PPU OAM. Our initial implementation is going to be really simple. When line ticks is greater than 80 on the OEM side, we just want to switch the mode to Xfer because that's the next mode. And that comes from, if we look at our Pixel FIFO in mode 2 OEM scan, it's 80 dots. After 80 dots, it jumps to mode 3, and so on. So we're going to do something similar for mode Xfer for now. For now, we're just going to be going through each of these states. And then for this one, it's going to be 180 or 80 plus 172, which is the minimum amount of ticks that the drawing pixels mode handles. Okay. And when we switch out of this mode, it's going to go to the HBlank. So we'll change this to HBlank. And for now, that's all we'll do with that. Eventually, we're going to set up the pixel pipeline, but in this initial video, we're just going to set up being able to switch to the different states. And jumping over to VBlank, I should probably do HBlank first, but I'll just do VBlank. So the VBlank is at the bottom. Once it's finished, all the visible lines. So in this one, if we're past the number of line ticks for ticks per line, then we're going to increment ly because we're moving to a new line. And remember, ly is our that's how we keep track of the current line. So, and now if the current line is greater than 154, which I should probably use a different variable name for that. For now, I'll just stick with 154, I guess. So that's going to be the number of total lines in a frame. So actually, let's go back to here. Yeah, lines per frame. I'm going to take this and put it in its place. So if ly is past the number of lines in a frame, then we know we need to go back to the beginning. And that first mode is OAM, so we're going to set it to OAM. And if we aren't past the ticks per line, actually, yeah, we also want to reset. Since we're starting back, we want to reset ly to 0. And we always want to reset our line ticks when we go to a new line. Okay, now we need to actually implement this increment ly. And the reason I'm making it a separate function is because there's certain things that happen when you increment the ly. So first, just ly++, but also we want to check that ly compare value. So let's see, if ly is equal to the ly compare register, so let's see, we want to set this to 1. Remember that lyc bit in the status register we want to set to 1. Otherwise, we want to set it to 0. Because that'll indicate to a cartridge, if it's trying to read that flag, that ly and lyc are equal. So now also we need to check the status of this interrupt. If sslyc is set, then we can throw an interrupt. And it'll be a lcd stat interrupt. If you remember, that's if that specific bit on the status register is enabled, that means they want to receive interrupts when this happens. So then we request an interrupt. So that would be the VBlank. HBlank is going to be kind of similar. See, PPU get context. Line ticks is greater than or equal to ticks per line. Okay, and you remember these are both going to have to implement handling when you're at the end of the line ticks, because HBlank happens at the end of that, but so does VBlank, because VBlank doesn't have the HBlank mode. If you look down here at the modes, you see 0 to 143, they all have this mode 0, but once it switches to mode 1, we still need to do all the same checks that we do at the very end with that mode 0. So we need to increment ly, at the end, and do the same checks essentially. And it looks like I'm going off the screen here again. I'll scroll it up again. So ly, if ly is greater than or equal to 144, which is yres, so that would mean that we are at the end of the line. Then we want to call a VBlank. That means we've hit the last line that is visible. So now we want to go into the VBlank mode. And we'll request a VBlank interrupt. And if the stat for SS VBlank is set, then we want to request that stat interrupt as well. Okay. Okay, now again we PPU get context, and we need to set the current frame to increment that, because now we're in a new frame once we're at the end of that HBlank. And of course we're at the last HBlank of that frame, so that's why we increment the frame counter. Now if we aren't past yres, let's see, we want to set the mode. Remember, if we're not at the last one, we just go back to the beginning, so we go to mode OAM. Okay, and we'll do PPU get context line ticks equals 0, because we're at the last part of this and we're resetting, just like we did in the VBlank. Now what I want to do is limit the frames, so how many frames that we get per second. In order to do that, I'm going to set up a couple of little variables here in this file. The target frame time is 1000 divided by 60 because I'm shooting for 60 frames per second. There's 1000 milliseconds in 1 second. I'm going to keep track of the previous frame time, timer that we're starting, and the frame count. So we're going to do this right after we increment the current frame. So the first thing that we're going to do is we actually need to make use of a function that doesn't exist yet too. So we're going to calculate the FPS here. So first we need to say end is get ticks, and get ticks we haven't done yet, so we need to implement that. It's going to be essentially the number of millisecond ticks since the program started, and SDL has a way to do that. So just like we have delay implemented in the UI code, we're going to implement get ticks in the UI code by calling SDL get ticks. Then I'm just going to put this in the common header up by where delay is as well. And going back to our PPUSM, so now that we have the current number of ticks, actually let's make that a U32. So U32 frame time equals end minus previous frame time. So this will give us the amount of time that was taken between the previous frame. So if that frame time is less than the target frame time, then we want a delay for that difference. So target frame time minus frame time. We want to delay that many milliseconds so we can try to achieve roughly 60 frames per second. So if end minus start timer is greater than or equal to 1000, that means we're on the next second. So I'm going to do some calculations for the FPS here. So FPS equals frame count, start timer equals end, frame count equals 0. We're going to printf the FPS here. Again, I'm going off the screen here. Let me move up. I'll scroll this up in a second. Sorry, it's gone off the bottom of the screen again. Okay, so yeah, now we're incrementing the frame count and setting the previous frame time to the number of ticks, the current ticks. So hopefully that'll make sense to you there. So let's try to make this. We got a couple of warnings. I might as well just go through and fix these. First off, this should just be D, not LD. Looks like I got something in DMA.c and instructions.c. I'll just go through and fix those as well. Get rid of that sleep. Actually, get rid of the whole section. And then instructions.c is, now it looks like it's missing a header. So I'll just add bus.h to that. I don't know how that one got by us. Just we haven't compiled it in a while. So let's make, okay, looks good. And let's see what happens when we run this. Let's run it against Dr. Mario. Okay, still nothing kind of happened there for Dr. Mario. 01 special, showing up fine. It's clear. And actually I'm going to jump over to our emu.c. So let's see, down here where we're calling UI update, we don't need to call that every single 1000 microseconds essentially. So now we can just call UI update whenever a frame changes. That'll at least improve the performance of the game. So let's create a previous frame 0, and we'll say if prev frame is not equal to PPU get context current frame. Okay, that's when we're going to call UI update, only when the frame changes. And prev frame equals, again, that PPU get context current frame. Alright, so now also in EMU cycles we actually need to invoke the PPU tick, so that needs to go right where timer tick is. So PPU tick will now get called every time the timer gets called. So now actually if we run Dr. Mario, let's rebuild it again. See, our special one runs fine. And if we run the Dr. Mario one, see a bunch of unsupported bus writes, but you see we actually have all of our debug information there. And actually, you see we have some animations going there too. See all these bus writes because we haven't implemented all the I/O yet. So, but you see we got some things animating in our debug window. It's kind of cool. So that's going to be a good start. And that's probably it for this video because it's getting kind of long. In the next video I'll go over the pixel processing pipeline, and then we'll get into actually rendering the background for games. We'll start with the background rendering because that'll probably take a little while, so I don't want to try to implement everything all in one video. So we'll do background and then probably sprites and windows after that. But I think that's a good stopping point for this video, and I hope you enjoyed everything. If you have any questions, just comment on the video, join the Discord channel that you'll see in the description, and like, subscribe, and all that. And thanks for watching.